All right, so last time, right, we were talking about what is a derivative, right? And we found it to be equal to this limit definition of a derivative right here, this guy. The derivative is the slope of a tangent line, which is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h, right? This is us simplifying it, and it comes out to this simplified form. But of course, what does that all mean if, if we're looking for a derivative? What is all this, right? And we saw that if we're looking for a derivative, we're basically calculating the slope, right, between just a tangent line here. But before we can get to the slope of a tangent line, to calculate the slope, we needed 2 points, right? And a tangent line by definition is just 1 point. So I couldn't technically just do the slope of a tangent line by itself, right? If I did the slope of a tangent line by itself, I'll be looking at just a single x1 and a single y1 point. And if I try to calculate that, I get y1 minus y1 over x1 minus x1. And we ended up with this whole 0 over 0 thing, which was undefined, right? We could not calculate the slope of a tangent line by using this formula here because it wouldn't work. We need 2 points. And by definition, the tangent point is just 1 point. So what we did was we calculated a bunch of secant lines, right? We calculated a secant line, by the way, is just a line that has 2 points that goes through a function, right? So we picked 2 random points. We called one an anchor point, and we called one just a slider, right? And we calculated the slope of that secant line all the way through. And when we were doing that, we came up with this general equation here for a general function and a generic function and a generic slider point, right? A generic slider point. And what we saw was that the secondary point was always this like h value away from our anchor point. Right? We just didn't realize that, right? We would say like, oh, if our anchor point was 3 and I was looking for my slider point to be at 10, my h in that case was 7, right? It was 7 units away, right? And if I changed it up and I said, oh, my slider point is 8, my new anchor point would then be, my old anchor point is still 3, so my h would be equal to 5. So h was just the value that would calculate how far away your anchor point is from your slider point, right? So h could be any value, positive or negative. It would just move your slider point around your anchor point, right? And when we did that, we would calculate the slope, and I had you guys calculate a bunch of slopes, right, for all of those secant lines, right? And then what we were doing was for a generic one, we came up with this right here, and we saw that if I had this right here, this equation, this would always calculate the slope of any secant line given any anchor point and any h value. Right? Any anchor point and any slide value to tell me what that h value should be, right? And then we applied what we learned from Unit 1, which was, well, what will happen if we took the limit as the slider point gets arbitrarily closer to our anchor point, right? It gets so close that it approaches 0. H approaches 0 there. And when h approaches 0, then that just becomes a single point, right? And we found out, like, oh, just because the function, right, of this slope can't be defined when h is equal to 0 doesn't mean that the limit doesn't exist, right? The limit is what is it approaching itself, and what that thing is approaching is the slope of that tangent line, whatever that equals to, and that's what we call a derivative, right? The derivative allows us to calculate the slope at a instant, not between 2 points, but at a instant. It's just at that single point, right? And what I wanted to show you was this graph of that, okay? So take a look here. This is the x squared function graphed right here. And I also have graphed along with it the secant line. Do you see this blue dotted line right here? This is the secant line between our anchor point. For right now, the anchor point that we're going to be using is at 2, right? Just like our first examples that we did when we were calculating that. Okay? And then B, this dot right here, is going to be our sliding point, right? So I'm going to slide that along, and you can see the secant line that gets drawn between those 2 points. You see that? Now, the secant line that's being drawn there, I'm calculating the slope of it right here, right here. So when we were calculating our slope of the secant line when the sliding point was at x equals 10 and my anchor point was at x equals 2, you see here the slope that we got was 12, and that's the slope of this line right here, this dotted line. Okay? So as I decrease my b value, right, I decrease my h as well, how far away it is from my anchor point, right? So as I decrease here to, let's say, x is equal to 8, the distance away from my anchor point is 6, right? But look at here. The slope of my secant line is 10. That's this line right here. And the idea behind a derivative is, all I'm trying to figure out is what's the slope when the anchor point and the slide point are pretty much the same. You see that? When they're pretty much the same. And it's telling me I can't calculate the slope at that point because it is undefined right there, because it's 0 over 0 because of the same point, right? But if we applied limits, right? If we apply limits and see what does the slope approach as h gets closer and closer to 0, or as b gets closer and closer to a, right? What is that slope approaching? What is that value approaching? And that's what the derivative is. And that's what the derivative is. And I want to show you. The derivative is the slope of the line that is tangent at that point. See right here, this green line that I have drawn right here? If you guys look closely, let me take off these labels. Get out of the way. Okay, so there, if we take a look at this point right there, right, this green line is touching x squared at 1 point exactly, and we can see that there is a slope of the line right here, right? There's clearly a slope for this line right here, and that slope is equal to 4, right? That slope is equal to 4. But the thing is, though, how do I calculate that slope? Right? Do I just go to random graphs and just try to draw my line as accurately as possible so that it's touching at 1 point and then just count the slope out? That's going to be impossible, right? Not all graphs are drawn perfectly, and you're not going to be able to draw a tangent line perfectly every single time and hope that it is, oh, you know what, that looks tangent, right? So what we do, right, what we do is to get to this tangent line, we find the derivative. And the derivative is just the limit as 2 points get arbitrarily closer to each other, right? And calculate the slope of that secant line. That's all it is. That's all the derivative is. So let me show you again. So let's move that up here. And let's go ahead and bring this line back. So if you look closely, right, what is the derivative? All I'm saying the derivative is the slope of the line that's tangent to the graph at a specific point, right? So here's my anchor point right here at 2. Right, as I get this closer and closer, do you see my secant line, my blue line right there? What is it approaching? It's approaching the same line as that tangent line right there. And if I go to the other side, if I come from the limit from the left-hand side, do you guys see that it approaches the same value for that tangent line? You guys see that? It approaches the same tangent line no matter which way I come from the left side or the right side. So the limit of this thing exists. And the function, the tangent line is there existing at that anchor point as well. So the derivative, right, exists right there at that point. Even though our algebra explanation of what a slope should be used to calculate doesn't exist there, right? The slope right there, you can see it. It's undefined if I use this slope definition. But if I use the derivative to define it, you can kind of see it approaches that 4 value. Do you see that? It's 4.1, 4.2. It's getting closer. And the other side is 3.6, 3.7, 3.9. All the way up to where it's undefined. Does that make sense, guys? Like, what is a derivative? All a derivative is just the slope of a tangent line to a function, right? The derivative of a function is the slope value of all the tangent lines that are on that function. So now you'll say, is it always going to be at a fixed like anchor point? Like, no, we can move that anchor point. Look. We move that anchor point. We can move it to 3, for example. When we move the anchor point to 3, right? I hope you guys saw what happened as I moved my anchor point. Do you guys see the tangent line there? The tangent line moves as well, and so does the slope value, right? The value of the slope changes as I move my anchor point because my tangent line changes. In order for it to stay tangent, right, the line has to change, right? So if I move here my anchor point to x equals 3, you see how my new tangent line is this guy now, right? And the slope of this tangent line is now equal to 6, right? The slope of this now is equal to 6. And again, if I bring this back and I see my slide points here, right, my secant lines, it does the same thing. Look at the slope here. As I approach this guy right here, the slope of my secant line looks like it's approaching 6. And it's undefined at that point again. And again, if I come from the left-hand side, the slope of that secant line also approaches 6. And that's all the derivative is, right? It sounds like this complex calculus concept, right? Like, oh, what the heck? You're finding derivatives. But all the derivative is is just the slope of a tangent line, right? The derivative of a function is just the slope of a tangent line to that said function. That's it. Okay? So when you're finding the derivative, you're just finding the slope of the tangent line. I keep saying that over and over again, but that's all it is, right? That's all it is. So the function of a derivative, right, means that you can plug in values for your x values, and it will tell you what's the slope at that specific x value. So when you're calculating the derivative, you're getting a function that tells you the slope of all the tangent lines of a particular function. Okay? All right. Let's you know what, let's do a problem. Let's actually do a problem. Okay, so if you guys could, can you write this down right here? This is my first example that we're going to go over together right here. I'm going to go ahead and scroll this down a little bit so I have more space to work with right here. Let's go a little bit more. Give me a little more space. There we go. So let's say I was given a function y is equal to x cubed, right? And I was asked to find the derivative of y is equal to x cubed. Okay? So the limit definition of a derivative, right? I was told, right, is going to be equal to the limit. That's not what I want to write with. It's going to be the limit as h approaches 0 of f of x plus h minus f of x. And I'm hoping you keep it in mind, right? This is from that whole idea that it's calculating the slope of a secant line, right? And this is the secondary point. That's the first point right there, right? All being divided by, it's technically supposed to be this, but you don't have to write this down. It's technically x plus h minus x, but the x's always will cancel when we do this, right? This is my secondary x value, and this is my first x value, but the x's are going to cancel. And then the bottom, we're just left with h. And that's the limit of that's the definition of a derivative, right? Of course, if I'm going to write this out, I'm going to say I'm supposed to be finding the derivative of y. That's just really annoying, though. If I'm going to have to write that every single time, I have to write down the word derivative of y. So instead of writing down the term, this phrase right here, derivative of y, because if you can imagine writing that over and over again is going to get really annoying, we shorthand that. So instead of writing down this whole thing to say that's the derivative of y, we just write it down as y prime. Y prime is the notation that we use to show that little prime, that little tick mark is to show that we're looking at the derivative of y. So instead of writing down derivative of y, we just write down y prime. That's one way of looking at it. Another way of looking at it, and you'll learn these as we go along the way. This is one way of writing the derivative of y. Another way of writing the derivative of y is dy dx. And there's some more ways, but I'll just stop there before you get confused by just the notation, right? So just focus right now when you see the y with the little line there, the little y prime, just understand that you're looking at the derivative of y. Okay, the derivative of y. All right, so check this out. Here's my derivative of well, I need to figure out here, right? I have I'm dealing with it says f of x though, and I'm dealing with the y is equal to x cubed. So I'm just gonna go ahead and just say like, oh, I'm just gonna write this as a note right here. In this case, right, f of x is gonna be our y, which is gonna be our x cubed. Right, that's all we're using for this one right now. We're gonna be using x cubed as our f of x. So how do you calculate this? How do you simplify this out? We just start plugging stuff in. You ready? We just start plugging stuff in. So I would say that y prime is equal to the limit as h approaches 0 of f of x plus h. Well, the f function that we're dealing with is x cubed, right? Is x cubed. So I would just use my cube function, which is x cubed, but instead of x, I'm going to plug in what I have inside here. And what I have inside is this x plus h, right? So it should be x plus h cubed. That's what I have going on in here. Minus f of x, again, minus f of x, but f of x is just x cubed. All divided by h. All divided by h. All right? So, take a look here. I'm going to do this off on the side right here. X plus h cubed, right? I can't just leave it like this, by the way. Just like we learned in chapter 1, if I do direct substitution right now for my limit, I'd be plugging in 0 in for h, and hopefully you guys will see that this will be something over 0, which is undefined, right? So I know that this limit exists. I know that there is a value there. I just have to find it, and I'm going to do it by simplifying this out, and hopefully the h in the denominator will cancel out. Okay, so let's take a look here. I can simplify this whole thing right here. X plus h cubed, I can just write that out as x plus h times x plus h times x plus h. And I can just multiply this all out, right? Do you guys remember how to do this back in your previous classes, multiplying out polynomials, right? You do it piece by piece, right? We would multiply this out first, right? And multiplying that out right there, x plus h times x plus h is going to give me x squared plus 2xh plus h squared. Have I lost anyone yet? Are you okay? Let me know, guys. Don't just let me talk nonstop, because this is where, if you are confused, you gotta let me know. And if you're not confused, that's fine as well. But if you are confused, I'm talking to you. I need to know. All right, so check this out. No questions then on how I got this right here from just multiplying out the x plus h times x plus h, right? I still have one more x plus h to multiply. And I don't like using the box method. I like stacking my stuff. But if you want to use the box method, you can use the box method to multiply it all out. I'm going to stack it up over here and multiply them out this way. So h times h squared is h cubed, right? And that's a positive h cubed. This right here is going to give me a positive 2xh squared. And this last one over here is going to give me a x squared times h. Okay, that's me multiplying. The way I got this row right here was by multiplying by this h. Now I'm going to multiply the next one, which is going to be x times h squared, which is going to give me a positive. What am I multiplying? X and h squared. That's right. X times h squared. That's going to give me that positive one right there. X times 2xh is going to give me a positive 2x squared h, and then x times x squared is going to give me x cubed. And again, if you're confused on how I'm getting these guys, I'm just multiplying this with everything above it here. Most people use the Punnett square to do it. I just multiply it this way. Punnett square is fine as well if you want to do it that way. Or better yet, if you remember this is a special case. This is a x plus h quantity cubed right here. If you guys remember Pascal's triangle, I don't know if you guys ever learned Pascal's triangle or not, but that's another way that you could have done this. Because look, you end up here with x cubed plus 3x squared h plus 3x h squared plus h cubed. Pascal's triangle is that thing where you have the coefficients here, 1, 3, 3, 1, and the next would be 1, 4, 6, 4, and then 1. I digress. That's not important. But anyways, this right here is what I'm going to replace this guy with, okay? So the derivative of y is equal to the limit as h, get out of here, is approaching 0. And right here, this whole thing, this x plus h quantity cubed, I'm going to rewrite it as x cubed plus 3x squared times h plus 3x times h squared plus h cubed. This whole thing is going to replace that x plus h cubed. Of course, it's still being followed by minus x cubed. How you guys doing? This, of course, is all still being divided by h. This is all still being divided by h. All right. You ready? We're still not done simplifying it. Hopefully you guys can see that this x cubed right here can cancel out with this x cubed back there. And I'm going to be left with, you ready? I'm going to be left with the derivative is equal to the limit as h approaches 0 of 3x squared h plus 3x h squared plus h cubed, all being divided by h. Now I can simplify this even further. I hope you guys see that. Every single term in the numerator has an h, so I can cancel out an h, right? I can cancel out an h. Do you guys see that? I can cancel out an h from here. There's 2 of them here, so I can cancel out one of them. There's 3 of them here. I can cancel out one of them and be left with 2 and cancel that out with this one down here. Let me color code that so we can see. I'm canceling out 1h there, canceling out 1h there. I'm canceling out 1h there. I'm being left with 2 h's right there. Right? So we're almost done. We're almost done. The derivative is equal to the limit as h approaches 0 of 3x squared plus 3xh plus h. Can I plug in my limit now, doing all that algebra work? I did all that algebra work so I can get rid of that h in the denominator so I can calculate this limit, right? That's the whole purpose of this. I'm trying to calculate this limit here as h approaches 0. And now that I've done so, right, I can calculate this limit, right? I can calculate this limit. I can evaluate this. So y prime is going to be equal to, and I just evaluate this right here, and I have y prime is equal to 3x squared plus 3x times 0 plus, oh, that should be a squared right there, plus 0 squared. I can evaluate this limit now, and those zeros cancel out, and I'm left with my derivative now. My derivative is y is equal to 3x squared, and that's my derivative. Whew. I found a function that will always tell me the slope of a tangent line at any given x value for my original function, which is x cubed, right? So if I have graphed fx cubed, and I'm looking at a tangent line at a specific anchor point, and I want to find out what that slope of that tangent line is, I just look at this. I just look at this function. This derivative right here will tell me what it is. You ready for this? This is what I'm saying. Let's say I have the graph of y is equal to x cubed, right? I have a graph of it and it looks something like this, right? And I just pick a random point. I just pick this point right here. And I say, you know what? I want to know what the slope of that tangent line is at that particular point. Let's say that point was equal to 1. All I have to do then is go to my derivative, y prime is equal to 3x squared, and just plug in 1 in for x. And when I plug in 1 in for x, I'll get like, oh, the derivative at 1 is going to be equal to 3, because it will be 3 times 1 squared, which is just 3. So the slope of this said tangent line is going to be equal to 3. And that's all this derivative is. It's going to tell you what the slope of the tangent line is at any x value, And I think that's awesome, because check this out. If you look at it graphically, right? This is for x squared. Let me change this up. Let's go ahead and look at this. Let's turn off these lines right here. And let's look at x cubed, shall we? Let's look at x cubed. X cubed looks like this, right? And let's say my anchor point was at 1. Oop, right here. Let's zoom in here. Okay, my anchor point is at 1 right there. Okay, and I want to see the tangent line. The tangent line will look like this. See that? So I can move my anchor point. My tangent line moves along the way there. And check this out. What's my slope of that tangent line? The slope of that tangent line, it says it's 3, right? And we calculated it, and it is 3. And that's what that slope is. And if I wanted to pick it at a different anchor point, and I want to say, let's say x was equal to, let's say, 2, right? If x is equal to 2, let's go back and look at this work here. If x was equal to 2, I plugged in 2 to here. It would be 2 squared, which is 4. 4 times 3 is 12. Look at Desmos. Desmos is telling me, hey, the slope of that tangent line is 12. Desmos, of course, is a computer, and it calculates it for you. And you're like, Naki, can't we just use this computer to calculate it for me? And yeah, that's what we're going to do later on. But what I want you to see right now, though, is realize we can do this. We can calculate these things without the help of Desmos, right? We can just do this algebraically and figure out, hey, the slope of the tangent line follows these equations, and these equations is just the derivative, okay? And it's just, I just think it's an interesting thing to see, right? We no longer care about the secant line, right? We no longer care about it. We don't need it anymore, because, well, actually we do need it, but it's we care about the the limit as that secant line gets closer and closer to that tangent line, right? And that's all it is. But yeah, I don't know. If you guys want, you should play with you should Google derivative with Desmos, and you should play with this stuff. It's kind of fun. You can see like the tangent line. Let me turn off U as well. You can see the tangent line as you move a function across, move the anchor point across a function, and you can see how the tangent line works as it goes along the way. And what I say is neat is the fact that you can calculate the slope of this line just by using this algebraic equation that we just found right here, this 3x squared, right? So look, if I have my anchor point at -1, right? If I have my anchor point at -1, you plug in -1 into this equation. -1 squared is 1. 1 times 3 is 3. The slope of the tangent line at x equals -1 should be equal to 3. And when you go and look at the graph, right, the tangent line is clearly positive, and not only that, it's also equal to 3, right? So you can see when you have like a slope that's, that tangent line is at 0, but you got this slope right here, this tangent line right over here at 1, it's equal to 3 as well, right? And you can just move that along. It's just neat to see. Look at that tangent line go. Better yet, once you learn how to program this, you can just like have it autoplay, and it'll move the tangent line for you automatically. You can slow it down if you want. How do you slow it down? There we go. Let's go a little slower there. So yeah, it's just kind of fun to play with, right? But that's all a derivative is. A derivative is a function that will give you the slope of a tangent line to the original function, right? Derivative of a function is just a function that's going to tell you what's the slope of the tangent line at any given x value. Okay? All right. So let's practice. Let's practice. Let's find another one. Okay? Let's do another one. Let's find the derivative of another one. So I'm going to scroll down here, and let's do another problem. Okay? So let's give us some space here. I want some more space. Give me some more space. Give me some more space. There we go. So let's take a second here, copy this down, right? And let's take a look at this problem right here. Okay. So here's a function. Y is equal to 2x squared minus 3x plus 4. It graphs a parabola, right? It graphs a parabola. And I want to find the derivative of this thing. I want to find out what's the function that's going to give me the slope of the tangent line at any x value, right? So I write it down. The derivative of a function, y prime, is equal to the limit as h approaches 0, right, of a slope, pretty much, right? And the slope is of this guy right here, which is going to be f of x plus h, right, because that's my sliding point, minus f of x, which is my fixed point, divided by my x value of the sliding point, which is x plus h, minus my x value of my x point, which is just x. But again, I don't write all this down because in the bottom there, x plus h minus x is just going to simplify to just h, right? So that's my limit definition right there. I'm going to zoom in a little bit here so I can give myself a little bit neater handwriting. So this is my derivative, right? And I just have to simplify this limit to get what I'm looking for, right? So here we go. So y prime is going to be equal to the limit as h approaches 0. Now here's the tricky part, right? Here's the tricky part. I need to find out what f of x plus h is. Okay? My f function, of course, is going to be this guy right here. 2x squared minus 3x plus 4, right? So in order for me to calculate this limit, here we go. It's going to be 2x squared minus 3x plus 4. This right here represents my f of some stuff. Now what goes inside there? What goes inside there is going to be this. X plus h and x plus h. Why is that? Because that's what's inside here that needs to go inside the function, right? And on the side, just real quick, if you guys remember, if I had on the side here, let's say I had a f of x is equal to 3x plus 2, for example, right? If I was plugging in, let's say f of 3, you would plug in 3 wherever you see an x, right? So this would be 3 times 3 plus 2, right? And we've learned about this when we dealt with functions in the past, right? So if I had like f of 7, for example, then that would be 3 times 7 plus 2. And it doesn't really matter, right, as long as you know what's being plugged inside. So if I had, for example, f of, let's say, a star, right, then that would be equal to 3 times a star plus 2. Well, all I'm doing is plugging in x plus h, right? F of x plus h just means that I'm having the same thing, but instead of like a star or a 7 or a 3, it's going to be a x plus h that goes in there instead. And that's what's happening here. This is my x plus h function that's being written inside. Okay? So all I've done here is wrote down this function, but evaluated it at x plus h. So 2x squared becomes 2x plus h squared. Minus 3x becomes minus 3 times x plus h, because that x plus h replaces that x. Plus 4. There's no x there, so I don't need to put anything after that. And that's it. That's f of x plus h being evaluated with this function. Okay? And then we go on to the next one. Let's go on to the next one. Next one is going to be minus f of x, and minus f of x is just this guy right here, 2x squared minus 3x plus 4. Why don't I do anything and plug anything for the x's here for the second one? Because there's nothing inside here of this f of x. It's just x itself. So I'm just taking this guy and just plugging x in, which means that it stays the same, right? So this right here represents this function. Are you guys okay? Again, I'm going to ask, is anyone lost? If you are lost, you're probably not the only one, right? But if you don't want to ask, I'm not going to know, and I'm just going to keep going. But please ask me if you guys are lost. This, of course, is all being divided by h in the bottom there. And that, oh, Oscar, you're lost. Okay, thank you for asking. Thank you for saying that. Like, honestly, you gotta speak up, and you're probably not the only one who's lost, Oscar. So, where have I lost you at? Have I lost you at the very beginning of what the derivative of a limit is? Or I'm sorry, the definition of a derivative is? Have I lost you? The function's on the right. That's just some random function. I just made that up. I just made that up. So I was just using that to help me illustrate how am I plugging in this x plus h over here. So I was just making up a function, like, let's say, let's call it g of x instead this time. So if I had a function g of x was equal to like x squared, in this problem, what is the derivative? Which function? We haven't found the derivative yet. This whole thing is the derivative, and we're trying to solve it to try to find out what the derivative is. Back to Oscar, though, the functions on the right was just me trying to help you understand where I got this from, right here, where I got the 2 times x plus h minus 3 times x plus h plus 4, right? So if I had g of x was equal to x squared plus 3x, for example, right? And I ask you to evaluate it for g of 2, you would just plug in 2, right, wherever there's an x. Right, wherever there's an x. Oscar, are you following along there? This was just some random function I wrote on the side. So how do you start plugging into the yellow? Okay. So the original function is y is equal to this. I just, since the limit definition uses f of x, I replace the y with pretty much f of x. I'm saying f of x in this case is going to be equal to 2x squared minus 3x plus 4. Okay, so I'm just saying in this case, instead of writing it as y, I'm writing it as f of x, just to make it easier since my limit definition uses f of x. Waiting on the next part of your question. So how did I get this guy in yellow down here? Let's go to there then. The limit definition of derivative is saying that we're going to use f of x plus h minus f of x divided by h. F of x plus h is just telling me, hey, go to f of x and plug in x plus h. So I went to this function up here and I replaced everything that has an x with x plus h, because that's what's inside here. And why is that inside there? That's our sliding point back when we were calculating the slope of a secant line. Okay? Are you okay, Oscar? I don't know if that answered your question or if that just made it worse. Yeah? Okay. Again, thank you, Oscar, for asking that. I'm pretty sure you weren't the only one who was confused as to where I was writing this equation in yellow. Okay? Hopefully that helped everyone else out as well, seeing as how to get that equation in yellow. The equation in green, so the yellow is f of x plus h. What about the green? Really? It's like you were reading my mind, or I was reading your mind. The equation that's in green is this part right here. It's just f of x. Well, what's f of x? F of x is this whole equation right here. But what do you plug in for x? Just x, right? If I told you, hey, what's g of x? You would just tell me, oh, g of x is just x squared plus 3x. It's just whatever the function is. And that's what it is right here. Hey, what's f of x? It's just the function that we have right there. Does that make sense, Aurelie? I don't know if that does make sense or not. And of course, f of x, back when we were doing this for the other couple days, f of x was supposed to be our anchor point. It's where our point was fixed at, right? That was our anchor point. But f of x is just equal to what the function is. Okay, does that make sense, Aurelie? I don't know if that makes sense or that made it worse. Yeah, it just looked like in n or something other than x. Oh, whoops. That's just messy handwriting. Sorry, that's f of x. There we go. Sorry. Just spread out your terms and functions. Yes. So we can clearly identify them. Yes, I can. You want me to go back and erase it, or just starting from now, Calvin? Starting from now. Okay. Well, actually, that's what we need to do. We need to start simplifying this monstrosity out, right? It looks vertically compressed. Oh, write bigger. Okay. I can do this. My fault. So actually, yeah, that's a habit of mine. I've made it vertically compressed because it's a fraction and the whole fraction is within this limit. But let's do this on this next one. I'll make it bigger. I don't know if you know what I meant. I don't know either. Are you saying that it's because I'm writing too small, or am I not giving enough space between one line to another? I'm not sure. Yeah, I'm not giving enough line. Oh, okay. So let's space it. I'll space it out a little bit more. So let's go down here for this next line. So right here, the limit as h approaches 0. I'll give it a little bit more space. Yeah. Okay. So let's go into here in the second one. We're going to simplify this one right here. Okay. Gaps. Yeah. Okay. I'll put more space there. So let's go ahead and start simplifying these equations here, right? So right here, this is going to be in the first one right here. I'm going to put it down. It's going to be, let's put it with brackets here. There's going to be 2 times, this will be x plus h quantity squared, right? X plus h quantity squared, which is going to simplify out to x squared plus 2xh plus h squared. How did I get that? X squared plus 2xh plus h squared. That's what this is when you FOIL this out. And I kind of did that. You know what? Just to stop the risk of making you more confused, I'm just going to write it all out. X plus h times x plus h, right? Minus. Now, right here, I'm going to distribute, right? I'm going to distribute that -3 into the x and the h right up here. Okay? So this is going to be minus 3x minus 3h, right? Plus 4. All I'm doing right now is I'm trying to simplify as most I can, right? As I'm working this out, right? Up here, there's nothing to simplify inside the green except for the fact that there's a minus sign in front there. So I can just go ahead and distribute this minus sign, right? You guys okay with that? I'm distributing this minus sign into this polynomial right here. So this will give me a minus 2x squared plus 3x minus 4, right? All I'm doing is simplifying it as I work it out along the way here, right? This, of course, is all still being divided by h, right? This is all still being divided by h. What I was trying to show was that when you simplify right here, x plus h times x plus h, if you FOIL this, x times x is going to give me x squared. X times h is x times h. There's 2 of them, so it would be plus 2x times h. I'm sorry, I should have gave more gap again, but h times h is going to give me h squared, right? That's me simplifying this part right here. The x plus h times x plus h simplifies to this part right here, right? And now let's just rewrite this all down one more time, right? This is going to give you a little bit more space here. This is going to be equal to the limit as h approaches 0 of distribute the 2 up here, right? The 2 with this x squared, the 2 with that 2x h, and the 2 with that h squared. This is going to come out to be 2x squared plus 2xh plus, I'm sorry, 4xh. I messed that up there because it's 2 times 2, which is 4, and then 2h squared. All right. Hopefully I haven't lost you guys. What I've written down was just me distributing that 2 right there in the very top. I'm going to bring all this down as well without the brackets anymore because I don't need them anymore. This is going to be minus 3x minus 3h plus 4 minus 2x squared plus 3x minus 4. And this is all over h. I'll give you guys a second to write that down. It's a lot. I know. I know. And again, if you're feeling overwhelmed, don't worry. Right? This is a lot. This is not something that is like, okay, I don't get this at all. I'm dumb. No, it's not that. That's not the case. Right? This is very takes time. If you get it though right away, that's awesome. And if you don't, I just don't want you to feel deterred. Right? I want you to understand that this takes time to understand. And I was telling this to my fourth grade class. If you don't get it today, eventually you will get it. Yeah, eventually you'll get it. Why don't you need the brackets anymore? Because there's nothing to simplify with the brackets, right? There's nothing to multiply in front anymore. I had the brackets. I technically didn't need the brackets up here as well. I just put it there just to make it easier for us to see the two functions being separated, right? But once I distribute the negative sign for this one, I didn't need the brackets on the tail end anymore. And the ones in front, I don't need the brackets anymore just because now I want to try to combine the functions to simplify it, right? The functions were just, the brackets were there just to show the separation, right? But if by the way, though, if there is a number in front of the bracket, like a 3, right, that just means you need to multiply everything inside the brackets with the 3 as well. All right. Enough talking. Let's look at some simplification that we can do here so I can make this a little bit easier on the eyes, right? Make this a little easier on the eyes. So if I take a look here and I take a look and I see, hey, I have a 2x squared and a negative 2x squared. You guys see that? So those guys should cancel each other out, right? 2x squared, negative 2x squared. They cancel. Do you guys see anything else that might cancel along the way? You guys see anything else? Let's see. What else do we got that might cancel? The negative 3x and the 3x. Yeah, very good. Monica, Max, very good, very good. It's this one right here. Negative 3x, positive 3x. They also cancel, don't they? Is there one more? The 4 and the 4 and the negative 4. Good. You guys spotted that. The 4. Shoot, I already had that color. Let's go a different color. Let's go pink. The 4 and the negative 4. They also cancel. So what I should be doing is actually technically crossing these out. Boop, 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 and boop. That leaves us, right? Once you cancel all that out, that leaves us with the limit as h approaches 0 of 4xh. I should have wrote this in order, but meh. Plus 2h squared minus 3h. Oh, it's technically kind of in order still. All divided by h. Which, hopefully you guys see, there's an h in every single term in the bottom, in the top, along with one h in the bottom. I can cancel out a single h, can't I? I can cancel out one h here, one h there, and one h there. And you're going to be left with, I have more space down here. Actually, I'll leave it right here just so we can still write it. This will be the limit as h approaches 0 of 4x plus 2h minus 3. Can I evaluate this now? There's no derivative. There's no denominator now, right? I can directly substitute in 0 in for h now, can't I? There's only one place to plug in 0 in for h, right? Which is right here. I can plug in 0 into there now. And this limit, right, will simplify out to be equal to 4x minus 3. This whole thing is what the derivative is equal to. 4x minus 3. That's your derivative. That's your derivative. Meaning, right, if I wanted to calculate the slope of a tangent line at x equals 2, all I have to do is plug in 2 into this x, and I'll have my slope of that said tangent line. And that's all the derivative is calculating the slope of a tangent line at a specific point, right? I'll give you guys a second to write that down. I want to show you something. I want to show you this graphically as well, though. So let me, is this okay, or do you guys want me to zoom out so you guys can see all of it? Let me zoom out a little bit so you can see all of it. It's a little small, though, but hopefully you can see it this way. If not, let me know. I'll zoom it back in if you guys want to see it zoomed back in. But yeah, welcome to the world of calculus, guys. You found a derivative using the limit definition, right? Secant lines, right? Calculating slopes. Who would have known? The first thing you're going to be doing in calculus is just calculating more slopes. But now we're calculating slopes at specifically a instant, a one point, a singular point, instead of doing it with 2 points. Conceptually, how do we do it? We just took the limit as one got closer to the other one, right? And we simplified those limits thanks to all of chapter 1, and we got this. And what I'm saying is with this derivative, right, if I was looking for the slope of a tangent line, right, at x equals 2, all I'm saying is then, right, I just plug it into the derivative. So the slope of the tangent line would be equal to 4 times 2 minus 3. Oh, yeah, 4 times 2 minus 3, which is going to give me the slope of that tangent line should be equal to 5. All right, hopefully you got that down. Let me go ahead and switch this over. I'll put this back up as well, but I'm going to switch this over to the graph. I'm going to change this function now. This function is, where's my mouse? Hello? Oh, there you are. Aha. So I'm going to go ahead and change this function now. It is going to be 2x squared minus 3x plus 4. And there's my graph. You see it? It's a parabola, right? And this right here is my tangent line. And if I was looking for the slope at x equals 5, let's say, right? Was that the one I picked? Did I pick 5 or 2? No, I picked 2. At x equals 2, my anchor point then is just going to go down here to 2. Boop. There's my tangent line. You guys see it? And what I'm saying is the slope of this tangent line is equal to 5. And according to Desmos, that is true. The slope of the tangent line is equal to 5. Isn't that neat? Hope you guys think it's neat. You ready for this next part? You ready for this next part? What we found was the derivative, right? And the derivative is equal to 4x minus 3. You ready for this? 4x minus 3. Check this out. Check this out. Let me go down here. Let's do it down here. Let's say I have here 4x minus 3, right? 4x minus 3. Check this out, guys. Let's call this g of x. Right? So here's g of x. Right, and let's make that, it's red as well, but let's make that one. Let's keep it red. So here's the deal. Check this out. Give me 1 second. A comma g of a. This graph of 4x minus 3 is the graph of the derivative of 2x squared minus 3x plus 4. And look, at this point right here, it's 2 comma 5, right? Well, what's the slope of the tangent line at 2 comma 6? The slope of the tangent line is equal to 5. What this new line that I just graphed right here, this 4x minus 3, what this represents is all the slopes of any tangent line along the way. Like, what are you saying, Nakmi? What I'm saying is this. Check this out. If I come to here at whatever this point is, let's go with x equals 1, right? At x equals 1, the slope of the tangent line, you see how it's less than the slope at x equals 2? You see how the slope has decreased here, right? X equals 2 has a slope of 5. X equals 1 has a slope of 1. So it's a smaller slope, but you can see it visually, right? You can see it visually that that slope is decreasing. Well, look at the second line that I have graphed down there, this 4x minus 3. If you look at the points, those points are equal to, well, I'll leave it to you. What do you guys think that point represents? And we'll go more into this next time when we start looking at it. I just wanted you to see it right now. Does that look like something to you? Does that point represent anything? We'll talk more about it later. But today, I want to focus more on us doing this. So I want you guys to try one, right? I want you guys to try one. I want you to try this one and tell me what you guys get on this pair deck. I'll put the pair deck link into the chat right now. If you don't want to join that way, you can join through joinpd.com, and the code is ULYPKI. Right? I'm going to go ahead and put that problem up right now, and I'm going to put it onto this screen as well. So there's going to be two things I want from you. Right? There's going to be a few things I want from you. So I'm going to scroll over here. This is going to be the, let me zoom in a little bit here so I can get the right scale. There we go. So we're going to be doing from Desmos. I'm going to write that right there. And let me get the problem from there as well so I can do this with you guys and show you what do I want from you guys. You guys are already writing on there. So I'm going to use the limit definition to find the derivative. So let's go ahead and bring that over here. But here's what I want from you guys, right? Here's what I want from you guys. First thing up is I want you to write down on your own paper the limit definition for me, right? Which is y prime is equal to y prime is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. The first thing I want from you, right? The first thing I want from you is to replace the f of x plus h and the f of x with the function that we're working with, right? Replace the f of x plus h minus f of x with the function that we're working with. That's what I want. So what I want is what I would write down for this next line, right? The limit as h approaches 0 of, and tell me what I should write there. We're not even going to do the algebra part. I just want you to set up this limit for me. So can you guys do that part first? And I'm going to take a look at your pair deck answers right now. So tell me what I would have, and I'll give you a hint. It'll look something like this. All right, so tell me what's going to be on the top there for me. Just write it out for me. Let me see it. This is your time to try. Good. I see 20 of you guys in there. Are you guys lagging? Are you guys not able to get into the pair deck? There are 34 of you guys in here. I don't understand why you're messing up. My attendance is just not working correctly. But yeah, let's see it. Let's see it, guys. I want to see some answers. Very good, very good. All right. I might have taken way too long to explain this. It looks like the majority of you guys are actually getting this. This is good. Looking good, guys. Looking very good. Very good. Some of you guys are close. Some of you guys are close. You don't have to solve it just yet, Calvin. If you want to, though, you can. But you don't have to solve it yet. I just want the setup first. And then we're going to solve it. So, yeah, you're right. If you want to keep solving right now. So if you haven't written it out yet, this is what you should have. You ready? The first function is the f function, but evaluated at x plus h. So the first function is this guy right here. Y is equal to negative 4x plus 5, but evaluated at x plus h. So I would write this out like this. It would come out as negative 4 times x plus h plus 5. That would represent that part. Minus f of x by itself, which is just going to be negative 4x plus 5. And that would be this one. That's the setup, guys. That's what it should look like. All right, the derivative should be equal to the limit as h approaches 0 of this right here. Now, that's how it should be set up. And if you don't have that, go ahead and copy that down on your own notes, right? Don't worry about putting it in the pair deck. Copy that down in your own notes. And now what I want you to do is evaluate this limit like you did back in chapter 1. Simplify this out and evaluate what should this limit equal to as h approaches 0 of what we just wrote out right here. So can you guys do some algebra there, simplify it out, and then evaluate it as x approaches 0. And then let's see what you guys get as your answer, right? Once you evaluate this. So I want the answer. What is, that's a highlighter. I want what is y prime equal to once you evaluate all this. So go ahead and get in there. Evaluate this one out. See what you guys get. I'll give you guys let's go with 2.5 minutes for this because this will take a little bit of time. So 25-minute timer. And yeah, you guys go ahead. There we go. So in 2 minutes, I'll come back. I'm just gonna give you guys a heads up right now. Like, you guys are doing awesome. All right. If you haven't done so already, right? Hopefully you get an answer in there into that pair deck. Looks like a couple of you guys got the right answers, right? It was beautiful. It is beautiful. So once you have plugged in, right, and you set up the limit definition of a derivative, now we just do the actual calculation of the limit, right? We just actually start working it out. So how do you work it out? You just start simplifying it, right? Simplify it as best you can. And then try to see if you can evaluate the limit. Because I can evaluate it right now because I have a 0 in the denominator there. So I'm going to do a little bit of algebra here. So I have here the limit as h approaches 0. And I'm just going to distribute, right, this negative 4 in the top there. And when I distribute that negative 4, I'm going to have a negative 4x minus 4h plus 5. Distribute this negative sign as well. This is going to become a plus 4x minus 5. And this is all being divided by h. right? So all I did was just simplify the numerator there by distributing, right? And then I'm going to look for things that are like terms and cancel those guys out. So I have here a plus 4x and a minus 4x and a plus 5 and a minus 5. So this is going to simplify to, and I'm going to write this up here so I have a little bit more space. This is going to be equal to y prime is equal to the limit as h approaches 0 of negative 4h divided by h. Of course, what's going to happen to the h's there? They're, of course, going to cancel out, aren't they? H on the top, h on the bottom. So I'm left with y prime is equal to the limit as h approaches 0 of negative 4. Oh, there's no more h to plug in, so I can evaluate this limit now, can't I? So what is negative 4 going to be equal to as h approaches 0? Why, that's just going to be equal to negative 4. And that's the derivative. That's the derivative. That means that the slope of the tangent line at any x value is always going to be equal to 4. That's it. That's it. You feel okay? You don't feel okay? You feel kind of sick? How do you feel? What do you think? Are you still lost? And if you're still lost, that's okay. You're good, Max. That's good. Emily, you're good as well. All right. I get it. Okay, that's good. I actually get this. Why do you sound surprised, Sydney? Just some small mistakes. You should never say, I actually get this. You get this, Sydney. Oh, you're good. All right, let's do another one. Let's do another one. All right, let's see how you feel when we go to another problem. We got 11 minutes, so we got enough time to do one more. I'm going to switch the slide, okay? Here's the next problem. The next problem is find the derivative of 3x squared. Let me copy that. And I don't have enough space there, so I'm going to go ahead and scroll this further over here. Let's do this one. Right here. So first things first, start this off for me. Can you write what is the limit definition of the derivative of this one right now? All right. So I don't want the work on the pair deck. I just want the setup on the pair deck first. All right. Can you give me this part first? Can you tell me what is f? By the way, since this is f of x and not y, I would write this as f of. Wait, actually, I have this problem in here. This was actually one of my planned problems. There we go. There it is. So, sorry, that has nothing to do with you guys. That's just more of my notes. So, what I'm saying is, can you guys go ahead and give me the setup on pair deck for me? What does that look like when you set that up? Don't mind me right now. I'm just randomly making space on my notes. Okay. So since this isn't y anymore, it's f of x. The way we denote this as a derivative, we don't write it as f of x with the prime here, by the way. When I'm looking for the derivative of f of x, we put the prime right there in between the f and the x. Okay, we put the prime right there. So that's how we denote that this is the derivative and not the function. And to calculate it, I want you guys to set this up for me. The limit as h approaches 0 of, and tell me what goes where. What do I write? Okay. The limit definition of a derivative, I'll write that off on the side right here. This is going to be equal to f of x plus h minus f of x. This is all divided by h. So can you guys tell me how to set it up first? Tell me what should be written down. And then after you do that, you don't have to do the work on the pair deck. You do the works on the side and then give me the final answer once it's simplified after you're done. Okay, so set up the limit first and then work it out and then tell me what it is. I'm going to wait a minute before I give you the limit definition. So I want you to try that first on your own. And then after I write that out and you guys see what it is, you can start working, if you didn't get it already, you can start working on how to do it algebraically and simplifying that limit. Okay? But yeah, don't wait for me if you already got it. You can keep going. Right? If you already got it, you can keep going. It's beautiful, guys. Your setups are beautiful. Yes, yes, yes. Multiple of you are getting that part, that setup part, beautifully done. And I'm jealous of some of your handwriting that you guys are doing on there. Unless you guys have a touch screen or something, because some of you guys are just, it looks like you're ridiculously able to write that with your mouse. And I was gonna call out some of your names for like the impressiveness of your ability to write by hand, but there's just so many of you guys that are doing it. I don't know. It's beautiful. All right, let's take a look here. Or you could, I mean, keep working. If you don't have this yet, you can get it from me right now. The limit as h approaches 0 of this function, right? I would write this out as, I'll write this out as 3 times x plus h squared minus 3 times x squared. By the way, I don't know if you started to notice yet, but you don't really need the brackets sometimes. I just do it out of habit. I like to write the brackets down just to show me where one function ends and where the other function begins, but it's not necessary. It's just something that I do out of practice. It helps me to see the functions, usually when the functions get ridiculously long. Right, but this case is a short one, so I technically didn't need it. So that's the setup right there. That's all it is. Right? That's the limit definition of a derivative of 3x squared. Yeah. So I'm going to go ahead and give you guys, this one's going to take you a little bit more time. So I'm going to give you guys 3 minutes. I lied, we only have 6 minutes. So 2 minutes to find this. See what you guys get in 2 minutes. Then we're going to finish this up for today, and then we'll continue again on, when do I see you guys? Thursday? Yeah, we'll continue this on Thursday. Of course, that doesn't mean I might see you guys on tomorrow, right, guys? For your back to school night. You gonna stop by with your parents? Yeah. You're my AP class. I expect at least 10 of you, right? At least 10 of you with your parents. Stop by and say hi. Or at least show them the video of me. You know, just be like, hey, here's my teacher. He's okay. All right, I'm gonna stop it a little early, just so we have some time. Have you caught on yet that a lot of your calculus skills is gonna be dependent on your algebra skills? Can you simplify this so that we can evaluate this limit? How good are your algebra skills with this? So I'm gonna have here the limit as h approaches 0 of, up in the top right there, we're gonna have 3 times x plus h squared. And if you need to, write it off on the side and just do it somewhere on the side, right? X plus h squared is x plus h written twice. And we just FOIL this out. So x times x is gonna be x squared. X times h is plus x times h. And again, plus another x times h. And then the last one is gonna be plus h squared. When you simplify this out, these are my like terms, and this becomes x squared plus 2xh plus h squared. And that's what I have in here. That's what's going to be in here. So it'll be 3x squared plus 2xh plus h squared minus 3x squared. This is all being divided by h. Keep going. Distribute my 3. Boom, boom, boom. So this is going to be the limit as h approaches 0 of 3x squared plus 2xh plus h squared minus 3x squared, all divided by h. Notice what they have in common. 3x squared and a minus 3x squared cancel each other out, right? I have a h in the top. I have two of them in the, you know what? I'll just show the work. I don't know why I try to keep shortcutting this. The limit as h approaches 0 of 2xh plus h squared divided by h. I can cancel out 1h from each of these guys. This is going to be equal to the limit as h approaches 0 of 2x. Did I mess this up anywhere? I did mess this up. That's a 6. That's a 6. Yeah, thank you. Thank you, Eva. Thank you. That's a 6. My goodness. I almost made a horrible mistake. Horrible mistake. Good catch. Good catch. I was just checking to see if you were paying attention. See? It was a good job. You passed the test, Eva. You saw that. You saw that. Monica, same thing. You guys, you're just seeing if you're paying attention. That's all. That's all. Expect the unexpected. So what's the limit? What's the derivative as h approaches 0? It's just going to be 6x, and that's what the derivative of this function is equal to. It's equal to 6x. All right. Woo! Almost made that mistake, but you guys caught it. Yeah, you're right. You're right. If I'm going to do this, I'll do this right. There we go. Yeah. Man, you guys are too sharp. You guys are too sharp. That actually makes me super happy that you guys are paying attention and catching my mistakes. Makes it a great day, too. All right, guys. That's going to be it for today. Thank you for paying attention. Thank you for doing the best. Did I mess up anywhere else? 1h canceled out. It should be okay. We'll deal with this next time. Thank you again, guys. That's it for today. I will see you guys on Thursday. Right? I'll see you guys on Thursday. Unless